Hi, George Diamond here. Today we're going to look at the next video in our video series. Today we're looking at limits at infinity. Now in our textbook this is section 3.5. So we use the Larson text at my school. So this will be section 3.5 of the Larson text. This is video number 1. In video number 1 we're just going to be looking at some information on a PowerPoint. This is basically some class notes. A full set of class notes that my students will use for their calculus class. Now what you won't see in this first video is a bunch of examples. Now we're going to save the examples for video number 2. So if you want to see the examples, how to calculate limits at infinity, take a look at my second video. But this is more for just some notes and some information, vocabulary, theorems, stuff like this. So let's get started. I got my maroon shirt on today. Let's go ahead and take a look at limits at infinity. So now, limits at infinity, in this section we're going to look at the end behavior of a function on an infinite interval. So as x goes to infinity, what happens to y? Alright, so the end behavior of a function. So now consider this function right here. We're going to do a little rational function. So consider the graph of f of x equals 3x squared divided by x squared plus 1. So consider this function. Now, if you have a graphing calculator available, you could always take a look at the graph of this and you can kind of give you some idea of what the end behavior will look like. But I'm going to do a little chart. So I'm going to put a couple of points on a chart from our graph and let's see what happens as x gets larger and larger and larger. What happens to y? Or when x gets smaller and smaller and smaller, what happens to y? Now, I'm going to start off with 0. So 0. So we'll put x on top and y on the bottom, so x and f of x. So let's let x be 0. What is y? Now, so if x is 0, now if you notice your function, 3x squared over x squared plus 1, if x is 0, you end up with 0 over 1 in your fraction, which is 0. So when x is 0, y is 0. Now let's let x get a little bit bigger. What if x is positive 1? What happens to y? Now substituting 1 in for x will give us 3 over 1 plus 1, 3 over 2, which is 1.5. Right? So you can see when x is 1, y is 1.5. So y is getting bigger. Okay, what happens, let's let x get to be an even bigger number. So what if x is 10? So let's let x be 10. Now if we substitute 10 in for x, okay, the corresponding y value is 2.97. So 2.97. So now x is getting bigger and bigger. Now y is increasing also, so we went from 1.5 to 2.97. I'll tell you what, let's let x be an even bigger number. So we went from x is 0, 1, and 10. Let's let x be 100. And let's see what we get for y. So we substitute 100 in for x. Now that would give us 3 over 100 squared divided by 100 squared plus 1. So if you have your calculator, you can do this on your calculator. I already have it done here on my chart. But calculating this gives us 2.9997. So notice what happens now as x is getting larger and larger and larger. So we say as x approaches infinity, okay, y is getting closer and closer to 3. So you see it goes from 1.5 to 2.97. As x is 100 is 2.9997. So as x gets bigger and bigger and bigger, the y value is approaching 3. Now that's basically a horizontal asymptote of this rational function. So we say as x approaches infinity, the y value approaches 3. Now it never actually gets to 3, it just keeps getting closer and closer and closer to 3. So we're going to describe this, we're going to say this, describe this as the limit as x approaches infinity of f of x, our function, is 3. So the limit as x approaches infinity is 3, that's the limit at positive infinity. Now, what happens whenever x gets smaller and smaller and smaller? What happens when x approaches negative infinity? So, well, let's try one. Let's substitute negative 1 in for x. Okay, now you have 3 times negative 1 squared over negative 1 squared plus 1. Evaluating this gives us 1.5 again. Well, let's let x be even smaller. Let's try negative 10. Okay, we tried positive 10, let's try negative 10. Substituting negative 10 in for x will give us 2.97. Now you can see as x is getting smaller and smaller and smaller, okay, the y value is approaching, looks like 3 again. Okay, let's try negative 100. Let's let x be really small, right? So substituting negative 100 in for x, once again we get 2.9997. Okay, so we can say as x approaches negative infinity, the y value approaches 3 again, right? So from the left and the right, so we say the limit as x approaches negative infinity, according to our data here, okay, the limit is 3. So that's the limit at negative infinity. So keep in mind now, most rational functions, I guess all rational functions will probably have, typically have one horizontal asymptote. Now, irrational functions can have more than one, but a rational function like this, just a fraction, an algebraic fraction function, you may have, typically you'll have one horizontal asymptote. Now we're going to divide this up into two parts. First thing we'll look at is limits at infinity. Part 2, we're going to look at describe horizontal asymptotes. But let's get started. Now in our textbook, we have Theorem 3.10, limits at infinity. Now, so think about this as if r is a positive real number. Consider this fraction, the limit as x approaches infinity of c over x to the r. Now, once again, r is a real number, so x to some exponent, so c divided by x. All right, as x approaches infinity. Now, what happens to this fraction when the bottom of the fraction just keeps getting bigger and bigger and bigger and bigger? Now, the top of the fraction is still just a number c. So the top of the fraction doesn't change. So as x approaches infinity, c is still c. But as x approaches infinity, the bottom of the fraction keeps getting larger and larger and larger. Now notice what happens to the fraction. Okay, you got some number dividing by, as x, I guess if the bottom of the fraction increases without bound, the actual fraction itself is getting smaller and smaller and smaller, right? So we say is you get some number divided by an x value, or as the denominator gets bigger and bigger and bigger, the actual fraction gets smaller and smaller and smaller. So the limit as x approaches infinity of some number over x is 0. I said the actual fraction itself is going to get smaller and smaller and smaller as the denominator gets bigger and bigger and bigger. Now, what about negative infinity? The limit as x approaches negative infinity of c over x to the r power. Well, same thing. Okay, still 0. Now you want to kind of remember this because we're going to be using this little theorem quite a bit as we look at some of our examples here today. So, look at our first example. Now we have a couple of simple examples that we're going to just pull up on the PowerPoint and I'm going to point them out. Some of the more complicated examples we're going to save for the next video, right? But look at this first little example. Okay, what about the limit as x approaches infinity of 10 over x squared? Now think about it. The bottom of the fraction is increasing without bound. The top of the fraction is not increasing. As x approaches infinity, 10 is still 10. Right? But the bottom of the fraction is getting larger and larger and larger. It's increasing without bound. That means the fraction itself is getting smaller and smaller and smaller. So 0. Right? Remember our theorem. Right? So 0 as x approaches infinity. Same thing would be true for negative infinity. Okay, what about this expression right here? Okay, what about the limit as x approaches negative infinity of 5 plus 2 over x? Well, 2 over x. The bottom of the fraction getting bigger and bigger and bigger, the fraction approaching 0. So the fraction itself approaches 0, and that gives us 5 plus 0, which is 5. Right, so the fraction goes to 0. Okay, what about this one here? What about the limit as x approaches infinity of 2/3 times 1 over x? Well, once again, the fraction, the bottom of the fraction is getting bigger, the fraction itself is approaching 0. So we say the fraction is, the 1 over x is 0 as x approaches infinity. So you end up here with 2/3 times 0, which is 0. All right. Okay, let's try this expression here. Kind of an odd expression, but when we get into some of our examples, we're going to have to be able to evaluate this type of expression. So we're going to go ahead and do one here on our PowerPoint so you can kind of see what's happening here. Now we're going to find the limit as x approaches negative infinity of 3 plus 1 over x squared divided by 5 minus 2 over x squared. Now, notice what happens. Right? 1 over x squared goes to 0, 2 over x squared goes to 0, and you end up with 3 plus 0 in your numerator, 5 plus 0 in the denominator, which is 3 over 5. All right. Now, what about an expression like this? Okay, 2 over x squared divided by x squared. Now, what happens? Now, this time with this expression, you have to simplify the 2x squared over x squared and the 3x squared over x squared. So the x's are going to cancel out there. The x squared will cancel out in the numerator and the denominator of your little fraction here. And this will give us 2 minus x squared, 2 minus 2 over x squared divided by 3 plus 3 over x squared. And once again, the two fractions go to 0. So that one goes to 0, that one goes to 0, and we end up with 2 over 3 for the limit as x approaches negative infinity. But now in this case right here, we had to kind of simplify the two little fractions there. All right. Now we'll look at some examples in the next video on how to find limits at infinity. So some more examples. We're going to look at some more rational functions, and we're going to look at some irrational functions. And we'll actually try 1 or 2 trig functions. We'll try 1 or 2 of those. That'll be in the next video though. Now a little bit about horizontal asymptotes. Now most students that have taken pre-calculus, typically in pre-calculus, this is something that you look at in pre-calculus. So most students, when they come to take calculus, they've already seen horizontal asymptotes a little bit. So we're going to look at, first of all, let's define what horizontal asymptotes are. So that horizontal asymptotes, so the line y equals L is a horizontal asymptote of f, if the following is true. So if you have a function, all right, you take the limit as x approaches infinity of f of x, all right, so the horizontal asymptote is going to be that number. It would be y equals that number. Because remember, we were talking about a horizontal asymptote is a horizontal line that your graph only approaches, it gets closer and closer and closer to. Okay, now, what about as x approaches negative infinity? Right? So same thing, as x approaches negative infinity of your function, your horizontal asymptote will be L, or it'll be the line y equals L. So it'll be the graph of a horizontal line will be y equal whatever the number is. So this will kind of describe a horizontal asymptote. And like I said, with a horizontal asymptote, you simply get closer and closer and closer as x gets larger or smaller. Okay. Now, 3 cases. Now these are like shortcuts that we can use to determine the horizontal asymptotes of virtually any rational function. If you can't remember these 3 cases, these shortcuts, then you can always find the limit as x approaches infinity. But here's the first case. So 3 cases. Get a horizontal asymptotes of rational functions. All right, case number 1. All right, so here's the first case. And like I said, a calculus student should be able to look at a rational function, and just by looking at it, should be able to pretty much identify what the horizontal asymptote will be. So here's our first case. Let's say we have a rational function, y equals ax to the m over bx to the n. Where m is your exponent in your numerator, the highest degree, so m would be the degree of your numerator, n would be the degree of your denominator. All right, now, so the first case, we're going to have no asymptote if m is greater than n. So if the degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote. So if the degree of the numerator is higher than the degree of the denominator, we have no horizontal asymptote. All right. Now, let me show you a little example here. So I'm going to just pull up a little example on the PowerPoint here, and we'll look at some more on our next video, but we'll do a little example here. Okay, just see if we can find the horizontal asymptote of this rational function here. Okay, y equals 2x squared plus 5 divided by 3x plus 1. Now, a little trick here to simplify this. To find your horizontal asymptote, we're going to find the limit as x approaches infinity of 2x squared plus 5 divided by 3x plus 1. Now, to find the limit as x approaches infinity, what we do with a rational function like this, okay, we're going to divide every term in the fraction by the highest degree of x in the denominator. Now, in the denominator, you got the 3x, so degree 1, so we're going to divide everything by x. So we're going to do the 2x squared divided by x, then we're going to do 5 divided by x in the numerator. So everything's going to be divided by the highest degree of x in the denominator. Now, in the denominator, you have 3x divided by x, so 3x over x, that'll simplify to just 3, and then 1 divided by x. Now, what happens as you notice here, the x squared over x will simplify to just 2x. Okay, the two fractions, 5 over x and 3 over x, those go to 0, right? And here the x's cancel out, and that gives us just 3. So you end up with 2x plus 0 over 3. Now, think about this now. We're taking the limit as x approaches infinity. Okay, as x, so the x variable is in our numerator here, so the numerator is just getting bigger and bigger and bigger. the bottom of the fraction is 3. So it's still 3. It don't change. But the numerator is just getting larger and larger and larger. So what you end up with is infinity divided by 3, which is infinity. So that indicates that this is undefined. That indicates that there's no asymptote. So no asymptote. So you end up with infinity over 3, okay, which indicates there's no asymptote. All right. Case number 2. So case number 2. Okay, once again, let me describe our rational function. We have y equals ax to the m again over bx to the n. All right. Now we said in case number 1, we said if the degree of the numerator is greater than the degree of the denominator, there's no asymptote. Okay, well what if the degree of the numerator is less than the degree of the denominator? Or the degree of the denominator is greater than the degree of the numerator. So what if m is less than n? In this case, the horizontal asymptote will be y equals 0. So as you look at this, if the degree of the denominator is higher than the degree of the numerator, right? So if the n is greater than m, is bigger than m, okay, that indicates that the horizontal asymptote will be y equals 0. The line y equals 0, which is the x-axis. So that's simply the x-axis. So the degree of your numerator is going to be higher than the degree of the numerator. Then if that's the case, then just by looking at that rational function, you should be able to recognize that the equation for the horizontal asymptote should be y equals 0, which is simply the x-axis. Now let's do a little example here real quick. So take a look at this function here. So y equals 2x plus 5 over 3x squared plus 1. Now this time, the 3x squared has the highest power in your function here. The numerator is degree 1, the denominator is degree 2. Now remember now, as we illustrate this second case, okay, we're going to find the limit as x approaches infinity of this rational function. Now to do this, I said we can always divide by the highest degree of x in the denominator. Now x, and that would be x squared. So we'll divide everything by x squared. So let's do 2x divided by x squared. So you take the first term of your numerator here, divide that by x squared. Okay, let's do 3x squared over x squared. Okay, we'll do 5 over x squared, and then 1 over x squared. So we're going to divide everything by x squared. Now what happens, the x's will kind of cancel out. So this will cancel out. That'll reduce to 1. These right here are going to cancel out. So those will cancel to just 3. So those are going to simplify a little bit. And we end up with we end up with 0, 2 over x, which will be 0, and then 3 plus 0 on the bottom, which is just 0 over 3. 0 divided by any number is 0. So our horizontal asymptote would be the line y equals 0. Now that'll be the case, that will always work out to be 0. Anytime the degree of the denominator is bigger than the degree of the numerator, you always get 0 here. All right. Okay, let's try our third case, case number 3. Once again, I'm going to describe a rational function. Again, y equals ax to the m over bx to the n. So this is our rational function. Now, what happens if the degree of the numerator is the same as the degree of the denominator? Right? Now, if that's the case, then the horizontal asymptote will be the coefficient of the leading term in the numerator and the denominator. So the horizontal asymptote will be y equals a over b. Right? If the highest degree in the numerator and the denominator are the same. So if m equals n, then that indicates that the horizontal asymptote will simply be the coefficient on the leading term in your numerator divided by the coefficient of the leading term in your denominator. So the degree of the numerator is the same as the degree of the degree of the denominator is the same as the degree of the numerator. So that indicates our horizontal asymptote will be y equals a over b. Not y equals 0, but y equals a over b. All right, so this is our 3 cases. Now, calculus students should pretty much be able to look at an expression or a function, a rational function, and be able to tell whether or not, be able to tell by looking at it what the horizontal asymptote will be. Okay, let's look at an example of the third case though. Okay, find the horizontal asymptote. Now this time we're going to do 2x squared plus 5 over 3x squared plus 1. Now, I said to calculate the horizontal asymptote, I'm going to take the limit as x approaches infinity. Now, when you do the limit as x approaches infinity, we're going to divide every term in your fraction by the highest degree of x in the denominator. In the denominator, we got 3x squared. So the highest degree of x is x to the second power. So we're going to take the 2x squared, divide that by x squared. We're going to do 5 divided by x squared in the numerator. Let's do 3x squared divided by x squared, and then 1 divided by x squared. So what happens? So remember, the x squares cancel out. So those cancel, these cancel out. And that leaves us then in the denominator with, now the two fractions here are going to go to 0. So 5 over x squared goes to 0. 1 divided by x squared goes to 0. And you end up with 2 plus 0 divided by 3 plus 0, which is 2/3. So we say the equation for the horizontal asymptote is the line y equals 2/3. So if you graph that, it's going to be a horizontal line. Okay, that's the line that your graph will approach but never touch. It's just an example of the third case. And what I want us to be able to do, I want my students to be able to do, is by looking at this, they can recognize that, hey, the degree of the numerator and the degree of the denominator is both 2. Right? So the horizontal asymptotes will be 2/3. So simply the coefficients on your leading terms. Right. Okay, let's try this example here. Let's see if we can find the vertical and horizontal asymptotes of a couple of rational functions. Right, so we can do these here on our PowerPoint, and then we'll look at some more examples when we do video number 2. Okay, let's try this rational function here. So f of x equals 3x minus 2. Now we're going to try to find the vertical and horizontal asymptotes. So let's see, we do the vertical asymptotes here, and we do the horizontal asymptotes here. Right, so let's see what we get. So the vertical asymptotes and the horizontal asymptote. Now, the vertical asymptotes will be where the denominator is equal to 0. So we'll do x plus 3 equals 0, x equals negative 3. So we have one vertical asymptote here. Okay, let's get our horizontal asymptote. Now, pretty much everyone should recognize that the degree of the numerator is the same as the degree of the denominator. So the horizontal asymptote here would be y equals 3 over 1. So you got a coefficient of 1 here, or just y equals 3. So this would be the equation of our horizontal asymptote. And then once again, we're using our shortcut method. And if you can't remember the shortcut now, you're going to have to find the limit as x approaches infinity and divide everything by 1. But it's a lot easier if you can remember your shortcut. Okay, let's try a practice example. All right, now with this example, as soon as you see the problem, I want you to pause the video. I want you to figure out the vertical and horizontal asymptotes yourself, and then start it back up and see if you got it correct, because we're going to work it out. So here's a video, or here's the rational function. As soon as you see the function, pause the video, work it out, see what you get, and then start it back up and see if you got your answer correct. So here's our video. F of x equals 2x over 9 minus x squared. So go ahead and pause, and we'll see what you get. Okay, so hopefully you got vertical and horizontal asymptotes on both. So we'll do the vertical asymptotes. We'll kind of check to see whether you got this correct or not. So asymptotes. So the vertical and horizontal asymptotes. Now, the vertical asymptotes, you take 9 minus x squared equals 0. And you got to find the zeros of your denominator. And that's going to be your vertical asymptotes. This will be negative x squared equals negative 9. That's x squared equals positive 9. X will be equal to plus or minus 3. So there's two vertical asymptotes here, plus 3 and negative 3, right? So x equal 3, x equal negative 3, right? So two vertical asymptotes. Now let's take a look at our horizontal asymptotes this time. Now you notice just by looking at this now, you've got the degree of your numerator here is 1. So the degree of the numerator is 1. The degree of the denominator is 2. Now you notice the degree of the denominator is greater than the degree of the numerator. So in this case, the horizontal asymptote should simply be y equals 0. All right, so that's our shortcut. So this is just a little example how to find the vertical and horizontal asymptotes. And we get our homework. There'll be a couple of problems like this where you'll have to calculate your vertical and horizontal asymptotes, and it can be very handy when we get into graphing, right? You got to be able to recognize where you have a vertical asymptote and a horizontal asymptote. Okay, that completes video number 1. All right, stay tuned for video number 2. We'll look at several examples in our next video.